Dear trainees, I'd like to welcome you to the e-learning module on sanitary landfilling. In the following, we will take a closer look at sanitary landfills and the closure of dump sites. All right, let's dive right into building a landfill. Wait, where should it be located? The perfect site for a landfill meets two goals: minimizing environmental impact and ensuring social acceptance. Come on, follow me through the steps of finding an appropriate location. Oh, before I forget, these site selection steps apply not only to landfills, but to all types of waste treatment plants. As a first step, it is important to determine the basic requirements of the site. That means you have to analyze which types and quantities of waste are to be disposed of. Depending on the functions of the site, the area and infrastructure have to meet different requirements. Once you know what you need, you can start looking for possible sites. At first, we exclude all areas where landfills cannot be built. This is called negative mapping. Wanna help me? Let's see what we have here. Areas with surface water like lakes, creeks, rivers or dry riverbeds. No. Drinking water protection zones. No, no way. Flood zones. No. Protected natural areas like national parks. Nope. Residential areas, industrial areas, airports. Also no. Valuable agricultural land, in most cases, no. Protected historical and cultural sites, no. Tourist attractions, also no. Afterwards, evaluate the remaining areas. They need to be of an appropriate size and accessible. They should not be located too far from the center of waste generation. And there needs to be electricity and water supply. On this basis, all areas are ranked. Only the 2 or 3 best ones are evaluated in detail. This is the positive mapping part. To get more detailed information, you need drillings and geotechnical investigations. It is important to examine the geological barrier as well as distance from and flow direction of the groundwater. The soil composition has to be determined and you have to look for protected flora and fauna. Found the perfect spot? Let's design the perfect landfill. The most common types of landfills we know are hill-shaped landfills, slope landfills, and pit landfills. There are two main issues in landfill design. First, the choice of sealing system, and second, the design of the leachate drainage system. The goal should be to drain the leachate by gravity without pumping. That means we have to avoid pit landfills. The lifetime of a landfill should be at least 15 years to ensure secure waste disposal. In addition, the selection and infrastructure of a new landfill cost a lot of money and time. It's better to build few big landfills than many small ones. Of course, the required landfill volume depends on the quantity of waste delivered. And other factors influence its size too. For example, additional material like intermediate cover layers or the space needed for internal roads. And don't forget the waste density. The higher the density, the more waste I can store in the same place. To reach the highest possible density, your landfill might need compaction equipment, for example, a compactor. Many international experts work with average waste density values to simplify calculations. The waste density of municipal waste is 0.8 to 1.2 tons per cubic meter. So the average those international experts use for calculation is 1. But, and this is very important, the density should be even higher. The waste on top of the landfill presses down the lower waste and increases compaction. In the depths of a landfill, densities of 1.5 tons per cubic meter can be reached. As a consequence, you can dispose of up to 50% more waste on a site than the calculation typically indicates. Another point to be considered in the design is height. The ground, bottom liner, drainage system, and so on cost money. Therefore, the landfill should be as high as possible to minimize costs. Big landfills should be designed for an average height of at least 15 meters, better 20 meters. The aim of sanitary landfilling is to minimize the environmental impact of waste. In order to protect the environment, 3 barriers must typically be planned. Barrier 1. The waste to be disposed of must be pre-treated and inert. Typically, pre-treatment enormously reduces potential emissions. Barrier 2 consists of technical barriers like bottom liners and capping systems. Barrier 3 is a geological barrier. The site should be in a location where the subsoil is as dense as possible. This protects the soil and groundwater against leachate emissions. The ground should not be very permeable. There should not be groundwater nearby, and it should be able to absorb liquids if leachate emissions do occur. Here you see the schematic layout of a landfill with the following elements: geological barrier, bottom liner, drainage system, leachate collection and discharge, surface water drainage, embankment dams, access road to landfill, waste body, waste installation, landfill gas collection system, capping system, landfill gas collection pipe, groundwater monitoring, plants for recultivation. As already mentioned, it is important to collect the water which leaks out. The water comes from rainfall and the waste itself. This leachate is highly contaminated. That is why it needs to be treated and cleaned in special leachate treatment plants. Leachate should flow from the landfill to the leachate ponds by gravity only. At least 2 leachate ponds should be planned in case one needs to be cleaned or repaired. The geological barrier, bottom liner and drainage system make up the encapsulation which protects the subsoil from pollution. In general, these systems need to be effective, of course, but they also need to be resistant and durable. There are different options available. In principle, we distinguish between single liner systems, composite liner systems and double liner systems. A single liner system consists of one sealing element and a drainage layer above, which collects and removes the leachate. A composite liner system consists of 2 different sealing elements. For example, a synthetic geomembrane and a compacted clay liner. Combining elements is intended to make use of the advantages of both types of sealing elements. Double liner systems have 2 sets of sealing elements and drains. They can be made of mineral or geosynthetic products. These systems are used in some countries for hazardous waste landfills. Bottom liners can be made of different materials. As mentioned before, they can be mineral liners like compacted clay liners. Other options are synthetic materials like geomembranes made of polyethylene, geosynthetic clay liners or asphalt. As you have seen, there are a lot of parameters which are important in landfill design. The types of waste, lifespan, volume, waste density and height, as well as systems to remove leachate and gas. But unfortunately, waste does not always end up on such well-designed landfills. There are also so-called dump sites, where waste is dumped uncontrolled. Improper waste disposal leads to soil, water and air contamination, which entails harm to nature, wildlife and human health. To prevent or eliminate these consequences, the closure and remediation of dump sites is of utmost importance. Before starting to close sites, some immediate measures are necessary. This includes investigations and monitoring programs. Construction of fences around the dump site might be helpful, but in some countries, such fences may not prevent entry, and the fences themselves may be so valuable that there is a high risk of them being stolen. There should be entry controls and warning signs to limit access to the area, and the general public should be informed about the closure. Then you can start closing the site methodically, following 5 steps. The first step is site registry. That means you collect all facts about the site. This database includes an evaluation of all source parameters, like information about the size of the site and the type of waste disposed there. Facts about the environment around the site are evaluated as well. For example, about soil, surface and groundwater. This evaluation helps determine whether there are already existing environmental impacts caused by fires, leachate or landfill gas. The further surroundings of the site and their use are also analyzed. These are recipient site criteria which answer the question, how is the land around the site used? Are there any residential areas or protected ecosystems? The goal is to determine whether human health, groundwater, drinking water or ecosystems are at risk. The second step is risk evaluation. A first assessment of risks is designed to distinguish between high, moderate and low risks. Potential risks are hydrogeological, landfill gas, stability, odors and health risks, as well as ecological risks. Different tools are available for risk assessment. With an expert's help and experience, crucial parameters are assessed and sites are categorized. In the third step, you focus on high and moderate risk sites. Detailed investigations are conducted. This requires the analysis of different samples, for example from special waste, soil, groundwater, surface and leachate water as well as landfill gas. To get this information, you have to dig deeper using trial pits, drillings or wells. On the basis of all these data, a quantitative risk assessment is conducted. Key questions are determined. If at least one of them is answered with yes, the dump site is directly classified as a high-risk dump site. Let's look at some examples. Was hazardous waste disposed of at the dump site, or can it be assumed that such waste was dumped in relevant amounts? Can the smell of landfill gas or other bad odors be detected at disturbing levels? Is the site located near groundwater wells? And must the generation of landfill leachate be assumed? If the answer to one or more of these questions is yes, these dump sites are immediately classified as high risk. Based on the remaining criteria, other dump sites are evaluated as high or moderate risk. Low-risk sites have to be verified. After finishing the evaluation, measures are defined for all sites. The closure of high-risk dump sites requires more complex measures. The design processes, allocation of financial resources and construction all take longer. The closure of moderate-risk dump sites requires similar measures. Only low-risk dump sites can be closed rather simply and at little expense. I recommend starting with the closure of low-risk sites. In parallel, you can start planning the closure of the higher-risk sites. In general, there are 2 closure methods. The first one involves securing waste ex situ. In this case, waste and contaminated soil is removed from the site. It is relocated to an appropriate landfill. This method is suitable for small dump sites, with a volume of maximum 5,000 cubic meters. It is a very fast and cost-efficient closure method, and the site is cleaned up after waste relocation. The second method involves the securing on the site in situ. The waste stays at the site but is kept. This means that the waste is covered by soil to prevent environmental damage. Landfill gas can be drained and collected by a layer of gravel or similar material. Another method uses gas drainage technology. After closure, the site should not be forgotten. Proper aftercare and monitoring is necessary. High and moderate risk dump sites should be equipped with a capping system as mentioned before. Depending on the waste type in the dump, this might include a degassing system. I'm sure you have seen how important it is to avoid uncontrolled waste disposal. To protect the environment, landfills must always be properly designed and operated. This also includes closure of dump sites which do not fulfill the requirements. Thank you very much for your attention.